All right, today we're going to be talking about calculating the inverse of a matrix. So before we get started, let's go ahead and just give a brief overview of what we're going to do and what it really means. So one good example is we might have an equation that looks like this. This is just an equation in one variable. And what this equation really does is it's computing the inverse of 1/30th. Now, with real numbers, this seems trivial. Again, it's just going to be 30. But I want to emphasize kind of the way of thinking of what's really going on when we're calculating the inverse. So with numbers, you know the inverse is just 1 over the thing, right? So we know that the inverse is just 1 over 30, which just happens to be 30, and that's the inverse. But what I want to emphasize is we can think of this a little more structured by taking this equation and doing it kind of slowly, one step at a time. So what we can do is we can multiply both sides by, say, 2. And that will reduce the equation to 1/15 x equals 2. And then we can multiply both sides by 3. And that will reduce the equation to 1/5 x equals 6. And then we can multiply both sides by 5. And we'll get finally the x equals 30. So what this means is we don't have to simply solve things in one fell swoop. We can kind of take our steps. And that's what we're going to do with matrices. Instead of just declaring what the matrix is and saying it's 1 over the matrix, we're going to do things one step at a time. And each of these steps that we're going to do are going to be these elementary row operations. So to do this, what we're going to do is in some sense, what we're really going to do is we're going to solve the equation AX equals I. And in this case, this X here is a matrix, and this I here is the identity matrix. So beforehand, we were solving for a vector, and now we're solving for a matrix. It may seem very weird, but it's going to work in almost the exact same way. So just like before, when we solved vector matrix equations, we took the unknown, in this case is the matrix X, and the equal sign, and we just turn that into a line. And so we're going to have an augmented matrix now. On one side, we have our A, and on the other side, we have our I. And if we can perform row operations little by little on both sides of this equation, albeit there's no equal sign explicitly, but this bar encodes an equal sign. If we can perform row operations and transform the A into an I, what is that going to say? That's going to translate into, if we get I equals something, what does this translate into? Well, this means that X, because this bar here, keep in mind this bar really mean X equals. So if we can translate the left into the identity and the right into something else, then what do we have translates directly into X equals that something. And we're solving for this X because what solves this is exactly A inverse. So if the inverse exists, keep in mind the only matrix that's going to cancel it out is in fact its inverse. So the only matrix that's going to solve this equation, if there is any solution, is in fact the inverse. And this is exactly what we're going to do. So let's go ahead and just dive into some examples. Let's do a nice 2x2 since we have an idea of what should happen. So we might want to calculate the inverse of this. So how do we do this? We're going to solve the equation that times a matrix, which is just encoded into that bar, equals the identity. And we're just going to solve. And we're going to apply some row operations to make this happen. All right, so what's the first thing we'll do? We're going to go ahead and try to get the pivot on this guy. So we're going to change that row. We're going to have the first row to make that a 1. And then what we're going to do is we have to zero out the one beneath it. So we already have this one, but we need to zero out the one beneath it. So now we're going to do row 2 plus row 1. All right. And we got the pivot. We have this one beneath it. And now we'll go to the next row. We want to get this one into a 1. So we're going to have that row. And finally, the only thing that's left is the pesky 1 above there. So how do we get that? We're going to get that by taking row 1 and subtracting row 2. Putting that into row 1. So let's be a little more delicate here. This is really 1/2 minus 1/4, 0 minus 1/2. And so altogether we have this matrix on the right. So this matrix here on the right should encode the inverse of what we started with. And so we can check it. Let's check. So keep in mind, how do you check something's inverse? So there is a formula. We could check it using the formula, and we'll do that in just a second. But I want to emphasize, how do you check if something's the inverse? The check is that we should be able to take A times A inverse and end up with the identity. And we should be able to take A inverse times the identity, A inverse times A, and end up with the identity. It has to work both ways. Now, it turns out if you're square, it doesn't really matter. But just for emphasis, it does have to work both ways. Just because you end up with an identity matrix does not mean you started with an inverse of each other, especially if the matrices you have are not square. So let's just check one of them for now. Let's check this one. So this says that if you undo something and then redo it, then you'll end up with the same thing as doing nothing. So what did we start with? We started with 2, 2 minus 1, 1. And we got 1/4, 1/4 minus 1/2, 1/2. So we're going to do some multiplication here. So that's 1/4 times 2 plus 1/4 times 2. Sure enough, that's 2/4 plus 2/4. That's 1. That's exactly what we want. We need to do the first row times the second column. And that's 1 minus 1. That's 0, just like we want. We need to do the second row plus times the second column. And sure enough, that's 1/4 minus 1/4. Rather, minus 1/4 plus 1/4. And then finally, we have the second row and the second column. And that's going to be 1/2 plus 1/2. And if we simplify all that out, we do get the identity matrix, just like we wanted. All right, that's one way of checking it. The other way of checking it is we know that the inverse of a 2x2 is equal to this factor, AD minus BC, times this funny kind of changed around matrix. So this is going to be 2 times 1 minus 2 times minus 1. So that's 1/4 altogether. This is a minus C, by the way. So this is 1/4 times 1, 1 minus 2, 2. And that's 1/4, 1/4, minus 1/2, 1/2. And sure enough, this matches what we got before. So that's two ways of checking it. But keep in mind, what we want to be able to do is compute the inverse of any matrix, not just a 2 by 2. But let's take a moment just to appreciate what we did. What we did is we took about 4 small steps. There's 4 small steps right here. Right? We did a row operation, and we did one smaller row operation, and another row operation, and finally another one. And just for emphasis, each of these row operations is really a matrix. So you can encode that one as a matrix. This one went into row 2. So you can encode this one as a matrix. This one scales the second row. And finally, this one is a multiple of the second row added to the first. And so each of these row operations is encoded by a matrix. So what we really did to find the inverse was we multiplied the matrices in order. We multiplied the matrices that performed this undoing in order. If you want, you can challenge, but if you multiply these 4 matrices together, you will get the inverse matrix. Just like at the beginning that I pointed out that to find the inverse, we're going to take some small steps. That's exactly what we're doing here. We're not doing it in one fell swoop, but we're doing it by steps. Just a few logical steps. Okay, so that was a nice, easy example. Let's go ahead and do a bigger example. So let's do a 3 by 3. One thing about a 3 by 3 is we can't check this using any nifty formula. There is a formula. It involves 9 variables instead of 4, but it's not as easy to use. It's not as obvious what that formula is. So we're going to attempt to compute the inverse of this matrix. So what are we going to do? We're going to go ahead and solve this equation. This is what we're doing, whether we realize it or not. And we're going to replace this x equals with just a bar. That's really what we're doing. So on one side, we have the matrix A that we want to take the inverse of. And on the right, we have the identity matrix. And when we solve for x, if the inverse exists, it will show up. We'll be able to do this. So when the identity is on the left, we'll get the inverse on the right. All right. So this one's just a lot of row operations, but it follows the same pattern. We're going to scale, and then we're going to try to add multiples of rows to each other to zero out more rows. And then we're going to repeat by alternating between these. So here we start with that one, and we're going to scale that guy to make it a 1. And then what we want to do is we want to zero out the other 2 entries. Now, in this example, it's really nice because those are already zeroed out for us, but ordinarily we'd have to zero these out. Just like the previous example, the 2 by 2, we had to zero that one out. But in this case, it's already done. So now instead, we can go ahead and think about moving on to the next row. So we already have the identity matrix in the first column right here. But now we're going to go to the second column. So we're going to have to scale that guy. So to do that, we're going to multiply by minus 1/2 row 2 and put it in row 2. I'm doing these kind of one step at a time. Again, when you get good at these, when you have enough practice, you can do multiple steps, but I'll let you know that these types of problems are very prone to error. So be wary about trying to take too many steps. It's better to write out more steps than fewer steps. So all we did there was we just halved that center row. So 1 became minus 1/2, and this one became minus 1/2. All right, so beforehand we zeroed out these guys. Now we're kind of lucky, but we still have to zero out that one. So we're going to change out row 1 minus 1/3 row 2. And that's going to go into row 1. So what do we have when we do that? That first row is going to become a 0 up here. All right, this becomes a 1/6, 1/3, and now we're going to take minus 1/3 times 1/2. You get a 1/6. So now the cool thing is we're almost getting the identity here. You just have one more column to go. So we need to scale that guy, the -1. So we're going to have minus row 3 go into row 3. So we're going to take the minus of the third row. So that becomes a 1. And the last one becomes a -1. All right. We have almost everything. The only thing we have left to do is to get these top two as zeros. So we have to zero those guys out. So we have row 1 minus 1/6 row 3 goes into row 1. And row 2 plus 1/2 row 3 goes into row 2. So what happens here? All right, so there's nothing in row 3 down here. That's just a 1. That stays as a 0. We chose the minus 1/6 here was chosen specifically to zero out this entry. So that's going to be a 0. All right, this is going to be a 1/3 because the bottom entry is still 0. This is still a 1/6 because that bottom entry is still 0. But this last one's going to become minus 1/6 times -1 is positive 1/6. Now the second entry, something similar is going to happen. We chose this plus 1/2 specifically so it would zero out with that one. So that's going to be a 0. This is still 0, so 0 plus 0 is 0. Minus 1/2 there. And now we have plus 1/2 times minus 1/2 is going to give us minus 1/2. And here we go. That's the identity matrix. So now if we go back and translate what this bar means, this bar tells us that our X, which is equal to A inverse, times the identity. So this is just the same thing as A inverse. So A inverse is equal to 1/3, 1/6, 1/6, 0 minus 1/2 minus 1/2, 0, 0, 1, or minus 1. Right, so this is a nice robust way to find the inverse. It's worth mentioning that if this sounds tedious and has a lot of steps, notice that every column, if you have a 3x3, for example, every column might have 3 steps. You have to scale and zero out. You have one scale step and n minus 1, where n is the number of columns or rows, n minus 1 zero out steps. So altogether, you're going to have n squared, potentially n squared steps going forward, and another potentially n squared steps going backwards. So this is very expensive. The larger you get, the more steps you're going to take. So it's not easy in general to find the inverse of a matrix. I would say that for computers these days, up to about 1,000 by 1,000 is fair, but even then you can run into some problems. But at least it's better than doing it by hand. So even though the inverse is important, it's worth noting that it is expensive even for you, or especially a computer, to compute. So before we end, let's go ahead and make sure our answer is right. And we can do that by just doing the check we did before. We're going to take this guy, and we're going to multiply it by the matrix that we started with. So we started with the matrix 3, 1, 0, 0, minus 2, 1, 0, 0, minus 1. And we have, we're going to do rows and columns. So this is 3 times a third is 1, 1 times 0 is 0, 0 times 0, so that's a 1. Right, we're going to keep going. Here we have 1/2 minus 1/2 plus 0. That's going to be 0. That's good. And then we have the last column. So 3 times a 6th is 1/2 minus 1/2 plus 0 times minus 1. All right, so far this seems to be checking out. Now we're going to go to the next row and the next column. So that's 0 times a third, 0 times a third, plus 0 plus 0. Then we go to the next column. What we have 0 minus 2 times minus 1/2 is plus 1. Plus 1 times 0. So that's good. We're going to the last column. We get 0, plus 1, and minus 1. And then finally, we have the last column in each of these. So here we have 0 plus 0 plus 0. So notice the last 0 comes from the fact that there's a 0 on the right. The next one, the same thing is going to happen. And finally, for the last one, you get 0 plus 0 plus 1. We have a minus 1 times a minus 1 gives us 1. So altogether, what we have, this becomes exactly 1, 0, 0, 0, 1, 0, 0, 0, 1, just like we wanted. So that's how you can find the inverse of a matrix. It's just small little steps using row reduction. Now, one thing I should mention, if you want to stop listening, you can, but this might seem a little weird. So I at least want to explain a little bit about another way to interpret this so it doesn't feel as weird. So what's really going on here? So keep in mind that when you apply a matrix A and you apply the vector 1, 0, 0, and zeros all the way down, this is just going to be equal to the first column of A. Right? And indeed, if you take the first column of A and you multiply this out, this gives you 1 times the first column plus 0. So the 1 comes from here. That's that 1. And the V1 comes from there. And then the next 0 comes from here. And then you get the next entry. Okay, so altogether, that's just V1. That's just the first column is what you get by multiplying A by 1, 0, 0, 0. And in much the same way, what should A inverse of this solves the equation AX equals that one. So this is the first column. What is this? This should be the first column of A inverse. Whatever the first column of A inverse is, it should be whatever you get by multiplying a 1 in the first position and zeros elsewhere. But by definition, this has to solve that equation. And in much the same way, you have A inverse, and you put 0, 1, 0. Whatever this is, better be the second column of A inverse. And this better solve AX equals the second standard vector. So of course you can go down the line. So what you're really doing by doing this, another way of doing it besides just solving a matrix equation with a big X, is what you're doing is you're simultaneously solving all of these equations. When you row reduce, you never actually care what's on the right. What's on the right never actually matters. So you're just row reducing A, and you're solving simultaneously all of these vectors as you do this, and just seeing what you get. And when you do this, you're going to compile all of those columns together on the right that are going to give you all the columns of A. So whatever this column becomes, when you're done solving, better be the first column of A inverse. And then you're simultaneously solving this AX equals the second standard vector, and whatever that vector becomes better be the second column of A inverse. And so if you repeat this, whatever's on the right better be exactly the columns of A inverse. And so one cool thing about thinking about it this way is it means you can actually solve multiple systems of equation, multiple systems of linear equations simultaneously, because the row reduction doesn't actually matter what's on the right. The only thing that matters is what the A is that you start on the left.